you want to verify the bars? Okay. Testicles, 1, 2. You good to go? Okay. Again, Shellcoding 101 by Data. And we'll get started right away. About me, you don't care about all this. I do programming, spoke at a couple conferences last year. Superhero in my off time. Before we go into this slide, I just want to say that prerequisite knowledge of assembly and Linux would be good, despite what you just saw. There is some... but yeah, we're not going to get into buffer overflows or anything like that. It's just going to be post-exploitation execution, that sort of thing. So what is shellcode? Traditionally, it's exactly like it sounds. It's code that spawns a shell, such as bin shell, bash, whatever you're into. Now it's kind of morphed itself into more of a payload. It's anything that you execute after taking control of a machine. And pretty much any exploit you're going to see these days is going to use this unless it's a overwrite a config file exploit. But all overflows, generally you're going to see this kind of stuff. And the one of the differences between it and normal assembly code is that it's single segment. So you don't have a data segment. You're only using text segment, as well as a stack and other things. But generally, it's as if you didn't have data to work with while writing the code. And again, only post execution hijacking. So why has it transformed into payload rather than just shell spawning? Bin shell does offer you the most general flexibility, but flexibility is not necessary. If you know what your target is and what you want to do, you basically can do everything you want with shellcode. You don't need to have a literal shell and all the overhead that's associated with it, such as logging or auditing or anything like that. It's also a much smaller memory footprint. You're not going to have your shell history in K-core, and less obvious because the generic way to look through memory is with strings, and much of shellcode is unprintable ASCII, and it'll just break strings halfway through, so you won't be able to see, all the stuff you're doing. You'll see random garbage that, will pretty much look like random normal memory garbage. And shell isn't always the best or the easiest solution. For example, you're exploiting a MySQL server. Generally, you don't want a shell. You just want all the data from that. And if you get file system access through the shell, you're going to have big, chunky files, and you're going to have to figure out all that sort of stuff. So in some cases, it's not always the best solution. And that's why targeted shellcode has kind of risen in popularity quite a bit. Oh, and feel free to ask questions. Just shout shit out. I don't really care. So the enemies of shellcode, network intrusion detection, generally through signature analysis, such as snort, that kind of thing. There's more host intrusion detection systems that'll do things like monitor what your process is actually doing on the system, file access, that sort of things. There's also IPS with sandboxing your incoming code so that it's watching it as it's executing. System customization. This is a big thing on Linux, not so much Windows, just because Linux and Unix are much more customizable down to the point where you can rewrite the entire system given enough motivation, I suppose. There's also protocol restrictions, which are probably, in general, the biggest problem for most shellcode. Buffer size is a big thing. Buffer size directly relates to versatility of your code. If you only have, X bytes to work with rather than a free range of whatever you want. And also there's character and opcode restrictions that may filter your incoming code and distort it to the point where it doesn't work at all, or to the point where it might crash the machine. So basic shellcode, again, single segment assembly and no null or restricted bytes. In some cases, this isn't really a big deal. It really depends, but in general, you should aim for no null or restricted bytes, because it's generally a requirement for certain types of overflows and most exploits. But again, not a rule of thumb for every single thing you're going to be doing. So the basic way to do this is just load data into assembly registers or using the stack, and then you call the Linux kernel to basically figure out everything for you past that. You could also do anything you can normally do in assembly for the most part, given your ability to do so through your code. So before we get into actually writing it, I feel like I should explain Linux system calls. System call, I suppose you could say, is basically a kernel API. And this instruction here, int 80, calls the kernel, and then based on what's in the registers of the stack at the time, it'll execute a command such as like run a system command or return your user ID, your process ID, that sort of things. And the basic format for this is the EAX register holds the syscall number, and everything else, including the stack, holds all the other parameters. Not always are you going to be using all the registers. Sometimes you might just use the stack. It depends on the exact thing you're trying to execute, because some things will have more arguments than you have registers for. So in that case, you have to use the stack. And all the, here, I'll show you. Basically, man2 is the programming pages. And you have all your codes. Like this is one of the syscalls. What is it? User source include? Yeah. Oh, that works. Oh, what the fuck was that? Okay. This file, or not. This machine appears to be neither. Oh, whatever. Don't worry about it. Basically, that file on a standard machine will have all the definitions of all the syscalls. So you can see the appropriate syscall and its number that should be loaded into EAX. And with man2, like if we do man2 execute, you see all the parameters that need to be passed to it. And from here, you could pretty much do whatever you want. It's just a little, working with it and understanding basic programming stuff that enables you to pretty much do anything you want as far as shellcode is concerned. So here's a very, very basic example, exit 0, seen in probably every program somebody's written. Man2 reports it as exit, and then takes one parameter as the status, which is just the return value. So again, EAX, syscall number is 1, EBX, return value. So here's our assembly that would do that. And remember, like some of this might not seem straightforward just because I wrote all this so that there's no null or restricted bytes and that kind of thing. So I tried to comment it as best I could, but if you're confused, then just ask a question, try and keep up, that sort of thing. First instruction here clears EAX, and then we copy 0 to EBX, which is the return value, and then we set EAX to 1. If you don't do this, it'll probably crash. In fact, it will, so by default. And then you just call the kernel, and the kernel notices that it's syscall 1, which is exit, and then does all the rest of the work for you. So, what is it? Mount SB drive. Okay, so you could just write it in just for testing purposes. Like eventually, you're going to want to run this through a C program just to make sure, like as a string, it's not crashing itself. But you could just write basic assembly and do it in NASM or GAS or whatever you want. But I just did Intel because I think it's easier to read for presentation purposes. But health, exit, and then link it. NASM compiles it into an object file. LD links it into an executable.
No, I want to know what the send.
Cute, cute. Yeah, that's going to compile it and then run it. Oh, great. Oh, there's no network connection. Never mind. Okay, you don't get to see an example. But basically, it would return whatever I set it to. And I think I just left it blank so that it returns 255 or 254. Everyone clear on this? Any questions so far? Okay, good. So writing to the console, same basic format, but you have more parameters, and it's a little bit different. I'm also using the stack in this. So basic format is write, and then the type of output, address of the string you want to write, and then the length of the string you want to write. So syscall 4 is write, output is 1 for standard out, ECX will be the string address, EDX will be the string length. And then afterwards, if you don't exit cleanly, it'll probably segfault, depending on the machine. But exit's only a couple bytes, so usually if you can, you should include it. So again, clear ECX, and then mul ECX is a assembly trick so that it's clearing EAX, ECX, and EDX all at once, so that you don't have to spend 6 bytes doing that with XOR instructions. And then we push the string to the stack in reverse. I'm really sad I can't execute these, actually.
Is the alphabet in
No. No. I don't want to waste time going through GCC and all that, but you guys can test these later. I'm sorry about this. So basically the string that I wrote says, hello, LayerOne attendees, and you push it in reverse, and then load up your registers with what you want and call kernel, and it'll dump that to the standard out. Pretty simple, not too hard to do. And so like I said, what you should do is you should have a little C program to run it through so that you know you're not accidentally putting in null bytes, which you probably should see if you're going to write it in hex, but just in case, just to make sure it works like this. And it's just a basic little format that basically just jumps execution to the start of the shellcode string and just does that. And if you have things that aren't supposed to begin at offset 1, you change this line here. You just add to it to wherever you want to jump to. Pretty simple, and you just use it as a template. So now we'll get into actual shellcode. Spawning a shell is EX, ECVE, and then parameters are the path to the actual thing you want to execute, the argument list, and then environment pointer if you want those variables included. We'll just run through this real quick. Clear out ECX. Push a null because you'll need a null for certain things, such as string termination. But doing this won't leave null bytes in your shellcode. They'll be all dynamically created when you actually run this. And then you push, again, string in reverse, and then point a path to this string. Push a null byte, which would end argv, and then move argv again. And then null out envp because you don't care about environment pointers. Call syscall11, which is ECVE. Call kernel, and you get a shell. You could optimize this by a few bytes by doing an assembly trick and basically setting EDX as a null and then just using that to push the nulls. But it doesn't really matter. It's only like 3 or 4 bytes you're saving, which is good in theory, but potentially not necessary. Here's another example that's pretty common for exploitation purposes is clearing IP tables. Here's a little complex exe CVE. And the only difference between this and the other one is that you have multiple parameters that you're sending to argv. So you have to sit there and null each one out right here and right here so that you know, basically knows when to end each argv thing. But again, it's not done within your actual shellcode bytes, so you won't have any null bytes from this. So basically, just push OXOB, the syscall number, pop it. CDQ basically clears EDX. It takes the unsigned bit in EAX and copies that to EDX, so that's a 1-byte XOR, which is, again, just a little assembly trick. And then basically the same format, just a bit longer because you have so much more to push onto the stack. And then set all those, and then execute with the kernel. There's one thing that I realized that I hadn't actually realized before from using shellcode. What's the problem with running this when you're trying to wipe out the firewall rules? Yeah, if you have a default chain policy on input, forward, or whatever, flush doesn't wipe that, and you can't use F and P in the same IP tables command. So if you really wanted to, you'd have to call bash with a -c and then do a really complex double AND to do both in one, which is a good exercise if you guys are starting to get into this and want to learn it.
double and only execute the second one, the first one succeeds.
True. But if the first one doesn't succeed, then the second one might potentially not succeed either. But yeah, and also one other thing that I noticed you could include. Actually, we'll get to that later. I'm getting ahead of myself. So advanced shellcoding. With just the basic knowledge of assembly and syscalls, you could probably do the majority of the things you want. However, complex NIDS or HIDS probably stomps your shellcode down in its tracks. And there's also, program restrictions such as ASCII restrictions, or they might be filtering your input data to the point that it's going to break the shellcode. So all these advanced features generally do a good job of either hiding the shellcode or working to make it more flexible in the face of scrutiny by the system. So first thing is ASCII or opcode restrictions. There's some protocols that will basically only accept ASCII, and despite how hard that sounds to not be able to execute shellcode in that, given that you only have this as your opcode range, it's relatively easy once you understand assembly to the point where you can do it. This is because assembly is pretty much the most flexible language that there is. And there's 10 ways to do one thing, and all of those will have different byte numbers and whatnot. So ASCII only is this range. If you stay below 7F, you're also Unicode safe. And then for specific 2 upper 2 lower calls, you have these ranges to work with, or to not work with, I should say. And then there's also protocol restrictions. For example, FTP has an end of message thing, and I believe SMTP does too. I don't know the exact byte. There's also a Control-C, Control-V, in the middle of a string may cause it to not work, or a semicolon, that sort of thing. Basically, just understanding of the protocol you're working with probably make this a moot point, because you could just plan your shellcode to not have these bytes in it. And then there's also a program called Dissembler, where given input assembly code, or hex code, I should say, whichever, it'll basically take that and run Ninja Magic, which is actually a command line option for Dissembler, is Ninja Magic. And it'll convert it to byte assembly that essentially doesn't use all the characters you tell it not to use. So it's very, very useful for ASCII only. But for those starting out, I'd say just go ahead and do it by hand to the point where it'll really increase your assembly knowledge, if nothing else. But that's a tool if you need to use it. It's very effective. So one thing I see is that a lot of people consider polymorphism to be encoding. Not the same thing at all. All 3 of these things are different. We're going to go into each one of these separately. But I just want to point out that these are definitely not the same thing. Some things have features that are similar, but the function completely different. So polymorphism is the ability of shellcode to be very different. The problem with a lot of NIDS is that while they may have a very reputable signature base, you could pretty much code up an assembly program that won't match any signatures that they have, given the extreme flexibility of assembly. It's hard to automate. Not too hard, depending on what you're working with, to do by hand, but it is time-consuming in some cases. 3 general areas of polymorphism are instruction usage, instruction order, and your use of NOPs. We'll get into each one of those right now. So again, instructions, very flexible. I put some examples that might be pretty common in just normal assembly as space-saving techniques, but they also demonstrate how flexible, move and XOR are 2 completely different opcodes, so they'll be, as far as just looking at the numbers you're given, indistinguishable to an NIDS, and there's really no way for an NIDS to deal with this, given the size of the database it's going to have to work with, and the overhead and processing required to, it's to the point where there's no way they're going to be able to run NIDS for millions potentially of byte combinations just for every single packet. No way that's going to happen, which makes learning polymorphism by hand very, very powerful, because you get to the point where NIDS generally isn't going to be very effective. So just some examples: clearing EAX, moving stuff. There's also more complicated, instead of say XOR is not a valid instruction for you, you could do things like and other types of logic instructions that generally produce the same results. Instructions order is also a very, very big thing. Interesting thing about assembly is that, in general, like most parts of your code are going to be interchangeable as far as where you could put the opcode itself. And here we have, this is the write I used earlier, and this is how it is normally. But generally, the only things that I need to keep intact is that these two instructions need to stay in this order, and these instructions all need to stay in this order. And these two have to stay in that order. Everything else can be moved around to the point where your hex output of your shellcode is going to look completely different. And barring an IPS sandboxing this, it's probably not going to be able to tell the difference. So, and on the right is just an example of it being, all rearranged while still maintaining functionality. Any questions? No? All right. Okay, so not padding. Not padding is actually the way most NIDSs will identify not just existing shellcode, but zero-day exploits, just because you put 100 OX90 instructions in a row, and it's going to be very, very easy to fingerprint. And the general rule of thumb is you want to put as many NOPs as your protocol will allow, or as your level of secrecy that is desired will allow. A NOP is an instruction that doesn't do anything. It stands for no operation. Basically, it's just filler. And most shellcode can put, the literal instruction for NOP is X90, but anything that doesn't affect your registers in a way you wouldn't want it can be used as a NOP. So this means I can move stuff, I can push to the stack as long as I'm not interfering with the things I've already pushed to the stack. I can decrement in registers, I can pretty much do whatever I want, like with the exception of jumping around in execution and that kind of thing. But like I said, dead registers are especially useful. In exit, we're only using EAX and EBX, so any other register we could throw bullshit instructions at, and it's gonna execute, and it's gonna look like it's doing something, but that's gonna have no effect on our final code other than execution time. And given how small most shellcode is, you can generally put a hell of a lot of NOPs. And most NIDSs do fingerprint based on NOP, and some even have gone to the extent of including things like Inc. EAX right here, or all the gray ones are NOPs, for the record. Any of these gray ones done over and over again, some NIDSs will actually account for the same instruction being repeated over and over. But again, you don't have to do anything like that. You could do anything that doesn't affect the registers you're working with, or you could even have them affect the registers you're working with as long as you accommodate for the changes when you actually want to execute the things you want to execute. So here's a polymorphism example with all three elements combined. I found a mad Wi-Fi exploit that I just, first exploit I picked, so that's the shellcode I'm using. And essentially all it does is write stop sniffing our network onto the attacker's terminal. Well, assuming mad Wi-Fi is being used by an attacker, but you understand. And then it exits, and that's all it does. So it's similar to the write that I had earlier. But it could be improved in a few areas. In all the examples I've shown you so far, we're generally using the stack. Because that, in most cases, will take up a bit fewer bytes, so you're saving yourself a bit of space. But more importantly, jump call is generally very easy to fingerprint unless you plan for things like, say you jump into a bunch of NOPs, so they won't be doing anything and you'll eventually hit where you want to jump. But generally, I tend to say that the stack is much more versatile, not only because you can move around the instructions much better, but you could also break them up so that you're pushing small pieces at a time here and there with lots of NOPs in between, making it even harder to figure out what's going on. But here's the original exploit. And I actually optimized it by 11 bytes by using the push in the write is actually at +1 byte because I have to push a word at the end, but I just threw on a new line. So in this case, the thing that you're jumping to, the string is actually longer to justify space requirements, but pushes allow you to move these anywhere you want as long as they stay in the order that you put. And again, you you could start pushing bytes or words, or as small as you want to do it and as numerous times as you want to do it, so that like these push instructions could be broken down into 30 different instructions, each with lots of nops in between it, so that it's very hard to determine what's going on just by looking at it real quick. So here's the original. On the right is the new one. I just put a few nops to demonstrate, but you could put quite a few more, of course, but I didn't want it to be size 3 font. But yeah, it's 42 bytes before I add the nops. So you got a lot of room to work with. Questions? Concerns? Okay, so we talked about polymorphism. Now we'll get into encoders. Encoders are, in a way, you could say they're a very, very simplified way of doing polymorphism on your shellcode. The problem is that your encoder is generally not going to be polymorphed itself, which is what separates encoders from polymorphic encoders. And the general way that encoders work is that they just push your shellcode to the stack, or however they want to get the address of them, and then they decode it while it's there, and then jump to them and execute it. So when you have your hex there ready to go in your exploit, and the victim network receives it, it'll just see a bunch of shit it doesn't know what to do with, and then a decoder. And unless it's sandboxing it, it's probably not going to know, what that is, just because even if you just add numeric 2 to every byte, they'll generally be completely different instructions as far as your shellcode is concerned. So again, easier than polymorphism, because all you need to do is write a working decoder. You don't need to work with instruction order, instruction usage, because the act of encoding generally does that for you. And it's very useful for quick and dirty upper and 2 lower evasion, just because your encoder is going to take up very few bytes, and you can work with that just to make an encoder that doesn't lie susceptible to these 2 functions or other functions like it. So here's an example, and I actually didn't convert this to Intel because I didn't want to deal with stack offsets and that sort of stuff. But just basically just push the shellcode, and then you have your decoder loop, and this shellcode is just it's the shellcode plus 1. So every byte is incremented by 1, and then the decoder just decrements every byte by 1, and then it jumps to it and executes. I actually think it got cut off, but there should be a return after this, but that's basic format. And polymorphic shellcode encoders, they generally automated, and they include features of both encoders and polymorphism. Examples are Shikata Ganai, which is the Metasploit basic one. I don't know if it's that anymore with the new version, but I think it is. Clet, and then AD Mutate. And at TourCon, Vlad presented a talk on shellcode polymorphism and encoders. And basically, his research synopsis is that they're all 100% detectable. And not in the sense that you just drop every packet that comes in, but in the sense that they're very, very easy to fingerprint, because not one of these actually properly implements any of the 3, well, I shouldn't say any, but all 3 of the polymorphism features. So in one way or another, they're very easy to fingerprint, either with instruction order or instruction usage or that sort of thing. Shikata Ganai, I believe, was the weakest, and I believe Clet was the strongest, but still 100% detectable, very easy to fingerprint, which is why I say doing polymorphism on your own, probably a much better solution than trying to work with the existing tools. I don't have an example of polymorphic shellcode encoders because they're like very long, and it's pretty much the same thing as an encoder once it's done. It's shellcode blending. Basically, it's spoofing the file type, and this is actually horribly simple to do. You could do it on the command line on your own. You just basically start your shellcode with whatever byte that your file header represents itself as, and then when somebody runs file on a suspicious binary, they'll see it as Amiga DOS data or RISC OS junk data, or there's all sorts. There's there's insane amounts of files, and lucky for us, open source leaves all of this information and exactly how it's parsed in etc file magic, or if you're using Fedora, for whatever reason, they put it in user lib RPM. You could look at that file, and you basically just pick a file format that you want, and it'll tell you exactly how to do it, even to the point where it'll tell you like subtypes of files. I really hope you have this file or I'm going to cry. Of course you don't have that file.
Might be Etsy.
In what?
Probably in the
Etsy what?
Etsy. Etsy now.
I don't use Ubuntu, so I have no idea what you're saying.
Probably under Etsy and Magic.
Magic? Ah, there you go. Come on. F. I apologize for this very much. Blame Ubuntu. That's what I'm going to do. You should have. Every presentation you go to from now on, everybody bring a laptop. But yeah, file contains all the information, and 5 magic contains all the ways it parses that file. So what I started doing actually last night was to make a little Python script that just pulls a random file type and dumps it into my shellcode, which may or may not be bad because I haven't made support for it not to start on bad instructions yet. But yeah, this file oh, come on. Lists all the information you need. I have an example. So a basic way to do this is in NASM you could just dump you just use DB for Intel. With AT&T it's like .byte or .whatever you're trying to push. You just define these, and this is an example of a zip header. And again, byte 5's variable. It'll determine file will report different types of zip formats or zip versions that are needed to unzip it. And the only thing you need to, like blending is very, very simple and should be included if you have the space for it, just because it'll add to your obfuscation, if it were, as it were. But the only two things you need to make sure is you account for modified registers. Like in this example, I need to account for the changes in EIX and EBX. Generally, I don't think this is going to be a problem because you're going to wipe all those anyway at the beginning of your shellcode. You should wipe all those anyway at the beginning of your shellcode. And make sure you don't start on opcodes that will segfault you. You don't want to be jumping into another program's address space because that'll kill you right away. You don't want to call another program's address space because it'll, all three of these things and a couple other specifics. But those are the three big ones. And if you don't know what opcodes these are actually producing, just NASM up your shellcode with these bytes at the front, and then you can use obj dump, object dump, to disassemble it, and it'll tell you in AT&T syntax exactly what assembly opcodes those are and what they're doing. So that way you can account for, I don't want to use this, or I want to make sure I jump to a different offset so that I'm not calling another program's address space or anything like that. Actually, I could probably do this. Is this a little endian, or is this a little endian machine? Okay. Yeah, I think this will be okay. Oh, what the hell. So there. See? That's all you have to do. And then if you wanted to do this, now it'll report as, I need version 9 to extract. Or 14 is, I need version 2.0 to extract. So there's literally that oh, I can't see it. It's off to the left. But it's like 15,000 lines are in that file. So there's like files that I don't even think I want to have reported just because they'll be suspicious in and of themselves with like, RISC draw data or, Intel motherboard code or random crap like that. But take a look at it, and it's very easy to do. Good way to obfuscate things. So one of the last things is anti-system customization. Again, Linux and Unix are easily the most customizable systems out there. And just changing your shell to like bin lol may be enough to stop a lot. It probably stop a hell of a lot of shellcode that's out there just because they're calling bin shell directly. But there's ways around this. A problem I ran into a lot was different systems like Ubuntu. I'm sure will list IP tables and what user sbin or some crap like that. I don't know if that's actually starting with a slash, but so you could do things like you're witching it, which will tell you the location of it, and that'll account for a bit of just distribution differences at the very least. And most systems, I think, almost all systems have which. And then there's also non-standard shell detection. Like, say you do move your shell to bin lol. I mean, that's fun and all, and I don't know how much of a headache that's going to be for your IT staff. But there is a way to detect that. Say as a user with your shell, you start a process in a proc. Your process ID/exe will be, or well, the parent of the process you start will be the shell. And the guy at this site named Itzik, he basically wrote shellcode that'll grab the parent process ID of the executing process and then see what shell started that and run it through there. It's a fairly compact shellcode for the insane amount that it does. I think it also like hides itself from PS and a lot of other random crap. But all this more or less depends on the level of information you have on the target system. If you don't know that they're doing this, it may be hard to target it this way. But generally, like things like which are generally a good idea, and it's just another way to attack a customized system in this kind of setting. So there's some resources that if you want to get into this or you're into this but you want more information, good books are Shellcoder's Handbook, which covers Linux, Solaris, and Windows shellcode. Hacking Art of Exploitation, which is being sold by No Starch Press over in the vendor's room, has a huge chapter on shellcode. Also goes over all sorts of overflows and generic exploitations. So if that's your weak area, I'd say definitely pick that book up. It's a great book. And then this is actually the only assembly book I've ever read, so I don't have anything else to recommend. But this is just by the guys that helped design these two chips. So I'd say get an assembly book too if that's your weak area. Sites like Millworm and shellcode.org will have publicly browsable shellcode archives, and you can go through those and get a lot of information. Basically, like a good way to get into this is just find a thing you want to shellcode, find a command you want to run, and just try and work it out. And based on the examples you can see online and maybe a book you get, you'll probably be able to figure out pretty quick. I don't think it's as hard as it looks. It's just assembly is a very foreign language to people who aren't familiar with it. But if you have a basic background in programming, it should be pretty easy to jump into. And then supplementary material, Linkers and Loaders is a great book. I just got done reading Memory as a Programming Concept, which is another great book if you want to learn more about the stack, the heap, how these things are created and used, that sort of thing. And then, again, general research of overflows and exploitations, also great supplementary material. Questions? I'll email them to the LayerOne people, and they'll be up on the site. Or if not, just can't read that. Just email me here, and I'll email it to you. I'll also email you all the associated files if you want to execute them and run them. They're all system safe. Worst case scenario is that they segfault or root your machine. Worst case scenario.
Datagram part, is that talking about just making it fit into one datagram?
What's that?
The title was Datagram Shellcoding.
Was it?
Up at the top.
I think it was by Datagram, comma, shellcoding. That'd be my guess. I don't know. I don't do the website. They run X, so I wasn't familiar. Can I go backwards?
Yeah, so what's your code run there?
What's that?
What's that run there? Is it that?
That's the thing that prints hello LayerOne attendees, which is actually quite long, only because of the enormous amount of characters in the string. Like I think the string is more than the actual code to print it. So, but yeah, is that it? I should probably just do this. So yeah, just thanks to LayerOne staff, Vlad for his polymorphic encoder research, Itzik for his blended shellcode research. He also does a lot of other crazy stuff like the system customization stuff, and his site is definitely a great resource if you're kind of intermediate at this and you want to see like more advanced applications of shellcode. He has stuff that does crazy stuff. Very good. His stuff's also up on Millworm, and then Lorcon for the exploit I thieved. No questions? No? Okay. Thank you. Oh, I'm just pulling this out. Thank you, sir.
No, no problem. Not a problem. Just unhook him.
Yeah.
Anyone know if this works? This one? Seemingly not.
I think it was.
Does that actually work? Yes, that's good.